Hi, welcome back to A Gal's Guide to the Ocean. This is our second episode, which we will be covering oceanic circulation for SLO2. You know us, you love us, your favorite host,
Catherine,
Yeah!
Woo, woo.
and JD.
Okay, so to know about ocean circulation, we need to first know the major ocean surface currents and how they're created. So the reason as to why and how these surface currents are created is due to the wind. The prevailing winds blow across the water surface, which is how the currents are made. The problem with this is that only 2% of the wind energy goes to the water, so this basically results in only like the top of the water being affected. So 100 through 200 meters of the water is the part that's affected. So with the winds, a circulation pattern is created in both hemispheres. This is where the currents flow east to west between the equator and 30 degrees latitude, west to east between 30 degrees and 60 degrees, and east to west between 60 degrees and the poles. The currents are eastern boundary. No, the currents are eastern boundary, and they come from high latitude areas, but they deliver cold water to the lower latitudes. When the currents combine, the gyres are created, and the rotation of these gyres also depends on the hemisphere. So in the northern hemisphere, they rotate clockwise, and in the southern hemisphere, it's counterclockwise.
Great information, Catherine.
Thank you.
I really love how everything always goes back to that 30-60 degree thing, the 30 increments. And since you left us off with talking about gyres, I wanted to know, I wanted to ask, or per se, state that one of the most common things with oceanic circulation is being able to, understand the gyre currents, and why they're more intense on the western side of the oceans versus the east. But first, let's start with, the basics. So, a gyre current, of course, is a large system of rotating ocean currents that are kind of created by the wind patterns, as well as forces made by the rotation of our planet. You know, our Earth is constantly spinning. And gyres form in some ocean basins, which we will discuss in later SLOs. Anyways, since they're surface currents, they typically move with the direction of the wind. Of course, that's impacted, but due to the Coriolis deflection, which we covered in the last episode, I believe, those currents are kind of offset at about 45 degrees, relative to the direction of the wind, and 45 to the right in the northern hemisphere, as well as the southern hemisphere. So, if you can remember 45 degrees, they're kind of slanted. That's the best way to put it. And we're going to put up some pictures for you on this podcast so that you can see exactly what we're talking about. But in the southern hemisphere, that one's going left, and in the right one, in the northern, it's going right. This is actually really important, and correspondent to our last episode, because those currents create a pattern of the east to the west, 30 degrees and 60 degrees. Now, the common question with gyres is, why are they stronger in the western hemisphere? Okay, so logically, that's because of the Coriolis effect. And the Coriolis effect is actually weakest at the equator, and so that's because of our planet's rotation, and sometimes it changes more quickly due to the latitude at the poles, not the equator. And also, not all is moved by west trade winds. Some piles along the west end of the ocean, and it's pushed east by gravity. So, of course, gravity is always going to be important to us. It's what keeps us down. And just to expand, it's also stronger because of the western intensification. Now, you're probably like, what the heck is western intensification? You're making up words. Well, actually, I am not. The most common way to put it is, it's a phenomenon of western intensification, and it's kind of a result of the Coriolis effect, and it's basically the tendency of currents along the western margins of the oceans, that are caused to be strong, swift, and narrow, But, however, this is the one downside, they tend to be more slower at the equator and slower and more diffuse in the eastern margins. So back to explaining how that works. The high latitude surface currents of the major gyres, they like go through a strong Coriolis type force, and so the currents move east, and that Coriolis force kind of deflects to the equator, which we talked about in the last episode, with a type of analogy with the sun. So they spread out to the deflection, and it doesn't really start till the current is on the western side of the ocean basin. And so the western currents must move through a narrow area, like a more narrow area, which makes it stronger. Like it's being forced in.
Okay, next we'll be talking about the Gulf Streams and their features. So Gulf Streams are warm ocean currents of the northern Atlantic Ocean off eastern North America. It takes the warm water and transports it to northwards along the U.S. East Coast. So the stream is a western boundary current, which is why it experiences western intensification, as JD talked about just right now. So western intensification makes the current become narrow, deep, and strong. It is known to be the fastest current in the world ocean with 9 kilometers per hour, and it can move large amounts of water. In addition to this, the stream is a huge help to Europe because it keeps Europe's warmer than it should, which results in there being no ice in the winter, which also helps with JD. What is it called when transportation of supplies and all that.
Next is one of my favorite topics, and it's the Ekman spiral. I'm basically gonna be covering the causes and effects. And the Ekman spiral kind of reminds me of like when you're trying to get, when they're trying to hypnotize you in that little spiral thing. We'll put a picture up of it. Very cool. And so this is basically the movement of successive layers, which then creates like a type of spiraling pattern or water motion, and this spiral typically goes about 100 meters down into the ocean. Now you're probably like, 100 meters, how is that relevant? I don't know what 100 meters looks like. So just to be aware, that's about 328 feet. Some people round it to 330, but more or less it's 328 before the motion dies out, because it dies out when it reaches the bottom. So the spiral is a direct cause of the consequence of the Coriolis effect, by the way, which the Coriolis effect is so important. And another maybe clear way to explain this process is the surface water moved by wind gets dragged down deeper layers of water. It drags down deeper layers of water below them, and so each layer is moved by friction from the previous shallower layer, and so each deeper layer that it moves more slow than the one before it until it reaches the 328 feet. So it starts off super strong, and then by the time that it reaches the bottom, it dies out. A potential effect, I guess, would be downwelling, which Catherine.
I'm going to talk about it. The next topic.
Yes. So downwelling, because it's also correspondent to the Ekman transport that moves surface waters to the coast, where it piles up and then sinks.
Okay, now for upwelling and downwelling, as JD mentioned earlier. So, upwelling and downwelling are a part of the currents. What upwelling does is bring deep water to the surface, which helps the nutrient-rich deep water go to the location where, it's deprived of nutrients. So, it's basically making that area be full of nutrients. Downwelling forces the surface water downwards, and this delivers the oxygen to deep water. The way upwelling happens is because of the surface currents when they separate from each other. This causes the deep water to go to the surface in order to replace the currents that separated, which is when the upwelling zones are created. And now for the creation of downwelling, it occurs when the surface currents meet, but it only goes down, which causes the surface water to sink.
That Catherine covered upwelling and downwelling. I feel like it's only best that we cover the locations of the major upwelling regions on our very favorite planet, which you guessed is Earth. Upwelling is the process which brings deeper water to the surface. It's kind of like the opposite of downwelling. And the opposite of the spiral, which I mentioned was my favorite part, and its major significance is bringing nutrient-rich deep waters to nutrient-deprived surface, which stimulates primary production. And it happens where surface currents are diverging. And diverging is just a really fancy word of saying moving in opposite directions from each other. And so the location that is mainly stated through our book is the equatorial Pacific. And that's basically saying like when the trade winds blow the north and south currents westward. So one of the regions is the Antarctic continent, where something similar happens like this. But with this, it's a little bit different because the west wind drift flows parallel, but it's like parallel in the opposite direction of the east wind drift. And there's other similarities like this that happen in different areas, and those areas would be near like northwest Africa, southern Africa, California, Oregon, Peru, Chile, Somalia, and even Oman. And that concludes our episode for today. Thank you so much for tuning in and
the
joining
end of
us.
SLO 2.
Yeah, woo!
Yeah.